Hello and welcome to Controllers Tech. This is the fourth video in the STM32 UART series, and today we will continue receiving the data, but using the DMA. We have covered how to receive data using the blocking mode, and using the interrupt in the previous video. Today we will use the DMA to do the same. DMA is mostly used to receive large data, so that the CPU can handle the rest of the tasks. I will demonstrate this in today's video, where we will receive some large data files via the UART using the DMA. We will continue with the same project from the previous video. Let's open the IOC file to make changes in the configuration. The basic configuration will remain the same, with baud rate of 115200, 8 data bits, 1 stop bit and no parity. We need to add the DMA. So open the DMA settings, and add the UART RX DMA. We will keep the mode normal for now, and the data width is set to byte. I have already explained these configurations in the video number 2. Make sure that the DMA interrupt is enabled in the NVIC tab. Click Save to generate the project. Let me clear the code from the previous video first. I am leaving this LED blinking as it is, so as to make sure the CPU is handling another task at usual rate. We will first see a simple receiving using the DMA. Let's define a RX data buffer of 20 bytes to store the received data. In the main function, we will receive data using the function whole UART receive DMA. The parameters are the UART instance, the receive buffer, and the size. Here I am only receiving 10 bytes of data. The DMA comes with two different interrupts. One is triggered when half of the total data is received, and another one triggers when the complete data is received. In our case, the receive complete callback is called when all 10 bytes are received, and the half receive complete callback will be called when 5 bytes of data has been received. Let's define two counters to check if the respective callback has been called or not. Inside the half receive callback, we will increment the half counter. Similarly, inside the receive complete callback, we will increment the full counter. The DMA is being used in the normal mode, so it gets disabled after all the 10 bytes have been received. So we need to make the call again inside the receive complete callback function. Alright, let's build and debug the project now. We will use the same configuration in the serial software. The baud rate is 115200 with 1 stop bit and no parity. I am going to send 1 bit at a time, and you can observe the RX data buffer in the debugger. Let's also add both the counters in the live expression. Each data byte is automatically stored in the next position in the buffer. Now I have sent 4 data bytes and both the counters are still 0. With the 5th data byte, the half counter sets to 1. This is because half the data has been received, and this is why the half transfer callback is called. Let's continue sending the data. Now all the 10 bytes have been received, and this is why the receive complete callback is called, and hence the full counter is also incremented. We restart the DMA reception at this point, and therefore the new data is stored from the beginning of the RX data buffer. The half counter increments again after receiving 5 data bytes, and the full counter increments after receiving 10 data bytes. We can send all 10 bytes at once, and both the counters will increment. So you can see how the DMA reception works. We can utilize these half transfer and full transfer callbacks to transfer the received data to another buffer, or to some file. We will see this in a while. Now I am going to demonstrate different reception methods under some scenarios. You can modify these methods as per your project requirement. I mentioned in the beginning that the DMA is mostly used when we want to receive large data via the UART. I have prepared some bin files which we will send via the UART. The file names are their actual size in bytes, and they just contain some numbers inside them. This makes it easier for us to track if all the data has been received. Let's assume a scenario where we want to receive certain data, and store it in a buffer. Also, we can define the buffer large enough to store the entire data. We still need to know the size of the data in advance, so we will first send the size of the data. This variable will keep track of if the size has been received or not. The size variable will store the size of the incoming data. Since we are receiving all the data in our main buffer, we don't need the half-receive callback. We will first receive the 4 bytes data for the size, and once all the 4 bytes have been received, the receive complete callback will be called. The same callback will be called when we finish receiving all the data bytes. So we need to write conditions which separate the reception of the size data from the actual data. The size received variable is set to 0 in the beginning, which means that the size data has not been received yet. So if this variable is 0 and the receive complete callback is called, it means that the 4 bytes size data has been received. We will extract the size value from the 4 data bytes. The value 48 is the offset between the number and its character equivalent. We receive characters in the UART communication, so we need to subtract 48 to get the number equivalent of the character. Now we have got the size of the data which is going to come next. Set the size received variable to 1, so that this loop doesn't run again. And set the DMA to receive the required number of data. As I mentioned, we are receiving the 4 bytes of size data in the beginning. Now the receive complete callback will be called again when all the data bytes have been received. And then we will set the size received variable to 0, and again start receiving 4 data bytes for the size. Basically we receive the size data, and set the DMA to receive the required number of bytes. Once all the data bytes have been received, we set the DMA to receive the size data again. This loop will continue to run forever. This entire scenario only works given that our sender sends the size first, and the receive MCU has enough space to store all the received data. Let's build and debug the project now. Alright, let's select the data file. I am going to send 2 kilobytes of data. We need to send the size first. Here it got received in the RX data buffer. Now we will send the file. You can see the RX data buffer has been updated with new values. We will check the numbers at the start and end of the buffer. The data starts with 510994. Let's open the binary file to check this. Here you can see the data starts with the same 510994. We have received a total of 2048 bytes, so let's check the data at the end. Here we have 135215. It is the same as what we have at the end of the file. So we have received all the data at once. Now let's select another binary file to send. This file contains 2044 bytes, so let's send the new size. We have received it in the RX data buffer. Let's send the data now. At the start we have 08672. Let's cross-check it with the binary file. Here we have the same numbers in the beginning. At the end of the RX data buffer, we have the numbers 135005. These are the same numbers which are present at the end of the file also. So we were able to receive a large amount of data using the DMA. This whole process can only work if the MCU has enough space to store all the data received in a single buffer. But what if the data to be received is very large, and we can't afford to store it in a single buffer. I am talking about the situation where you probably want to receive an audio file, or a video file via the UART, and store it in the SD card, or the flash storage. Here we do not want to create a buffer to store files in megabytes, as mostly the MCU does not have the space for it. So we will now see how to handle situations like this. Let's define the RX data buffer, which can only store 256 bytes at once. Now to keep things simple, I am defining another buffer, which can store 4 kilobytes of data. Think of this buffer as the space in the SD card or flash storage, where we want to store our file. The code will remain the same, just instead of updating the buffer, you need to update the file. I will explain this in the end. Let's define variables to keep track if the half transfer and full transfer callbacks have been triggered. The index variable will keep track of how many bytes have been written to the main buffer. We still need to receive the size data, so we need these two variables. We will first write the half transfer complete callback. We are now receiving the data in the circular mode, so the DMA can't be stopped in the middle. We will first receive the 4 bytes of the size data, and then continue receiving the main data. The half-received callback will be called when we have received 128 bytes in total, including the size data. Since the size data is always received at the beginning of the buffer, we can extract the size in the half-transfer callback function. It still is present in the first 4 bytes of the RX data buffer. After extracting the size, reset the index variable to 0. Now we will copy the main data, which starts from the 4th position in the RX data buffer, into the final buffer. Out of 128 bytes, 4 bytes were used by the size data, so we only need to copy 124 bytes now. Instead of copying the data to the main buffer, you can create a file in the SD card, and copy 124 bytes to that file. Now let's reset the first half of the RX data buffer. Now update the index variable to indicate how many data bytes have been handled already. The size received variable is set to 1, so that we don't enter this loop again. Now once the third set of 128 bytes are received, we will enter this callback again. This time we will update the final buffer with 128 bytes from the RX data buffer. Clear the first half of the RX data buffer, and update the index variable. Each time the half transfer callback is called, the HDC will be set to 1, and the FTC will be reset to 0. Now when the second half of the RX data buffer is received, the receive complete callback will be called. Here we will simply copy the data, starting from the 128th position in the RX data buffer, and store it in the final buffer. Then clear the second half of the RX data buffer, and update the index variable. We will also rest the HDC variable, and set the FTC variable. This entire structure works well if the total data is in the multiple of 256. But let's assume that if we are receiving 260 bytes, the half and full transfer callbacks will be called once, and the remaining 4 bytes will be stored in the first half of the RX data buffer. Since we haven't received 128 bytes, the callback won't be called. To handle this situation, we will write the reset of the code in the while loop. Remember that we still have the size of the incoming data, so we will check the difference between the size and the index variable. Our code will only execute if this difference is less than 128. This is because the difference can be large in the beginning, and this means that we are still receiving the data. When the difference is less than 128, this means that the last few bytes have been received, and the callback hasn't been called. Further, we will check if the variable HDC is set. If it is set, that means the HDC callback was called, and the extra bytes are in the second half of the RX data buffer. So we will copy the remaining data to the final buffer, and update the value of the index variable. Remember that we clear the Rx data buffer after copying data from it, so the string copy function works just fine. You can also use memcopy function, and copy the remaining bytes into the final buffer as shown in the image. Now let's reset the size received variable, so that the entire process can start from the beginning. Reset the HTC variable also. The DMA is in the circular mode, so it will continue storing the data into the next position in the Rx data buffer. We need to stop the DMA first, and then receive the data again, so that it can start receiving from the beginning. Similarly, if the FDC variable is set to 1, which means that the FDC callback was called, and the extra bytes are in the first half of the Rx data buffer. So we will copy the remaining data from the beginning of the Rx data buffer, and update the value of the index variable. If we receive the data in the multiple of 256, the index variable will be equal to the size. In this case we will check one more condition, if either of the HTC or FTC variables were set. This is because the index variable is equal to the size in the beginning, or when all the data is received. So we want to avoid those scenarios here. Here we don't need to copy anything, but we will reset the variables and start the DMA again. We have few warnings, and that is because the string copy function takes the character pointer as the parameter. Let me typecast these buffers. Alright, let's build and debug the project now. Let me add the final buffer to the live expression. Also add the index variable, and the size variable. Let's send the file with 2200 bytes. We will send the size first, and then send the file. The index variable is 256, which means we only received 256 bytes. Well, this is because I haven't enabled the circular mode in the DMA configuration. Let me quickly enable it. Let's build and debug again. We have received 2200 bytes now. Let's check if the data received is correct. The data starts with 63884, and ends with 2399. We have it here in the beginning. There were a total of 2200 bytes, so we should see the last data value at 2199. This is not the data we were expecting here. Here it is, ending at 2203. Basically we have the shift of 4 bytes in the final buffer. This is because I made a mistake here. Since we are copying the 124 bytes to the final buffer, the index value will increment by 124. Let's test it again. I will send the same file again. Here you can see the data ends at 2199 now. Let's send another file now. This file contains 2044 bytes, and combining the 4 bytes of size, the total data is 2048 bytes, a multiple of 256. We have received all the data successfully. Let's try sending another file. Here we have received 2176 bytes. So the data reception works well with DMA in circular mode too. As I mentioned earlier, the final buffer is defined just for the testing purpose. You can instead copy this received data directly to the file in the SD card, or some flash memory. All you need to do is, instead of this memcopy function, use another function to update the file. The parameters could remain the same. I will make a video to demonstrate this in future. This is it for the video. I hope you understood how the DMA is used to receive the data via the UART. I will continue the UART series, and in the next video we will see the idle line interrupt and DMA. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.